Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study, and it's my pleasure to welcome you here this afternoon to this Institute lecture. After the lecture, there'll be a reception to which you're all invited in Ford Hall. Today, our speaker is Peter Sarnak, who joined the Institute as Professor in the School of Mathematics last July. Peter obtained his bachelor's degree from the University of Witwatersrand in South Africa in 1975, and his PhD from Stanford University in 1980. He then joined the faculty of the Courant Institute of Mathematical Sciences at NYU, leaving in 1987 to become professor back at Stanford. In 1991, he came to the mathematics department of Princeton University, where he has been Eugene Higgins Professor of Mathematics since 2002. From 1999 to 2002, and from 2005 to 2007, he was also a member in the School of Mathematics here at the Institute. We were delighted last year when he agreed to join the faculty of the School of Mathematics at the Institute. He continues to hold his post as professor at Princeton University. Although he's officially half-time at both institutions, he's so energetic that he actually seems to be full-time at both institutions. Peter is the recipient of many prizes and honors, including the Levi-Conant and Frank Nelson Cole Prizes of the American Mathematical Society, and in 2002 he was elected to both the National Academy of Sciences of the United States and the Royal Society in London. Peter is one of the world's leading number theorists. His work has wide and profound implications in a number of areas of mathematics, from analysis to mathematical physics, crossing boundaries between specialisms within the subject. Today's title is Solutions to Equations in Integers. Peter.
Thank you. Well, thank you very much. It's a pleasure to give this lecture. It's working, right? I have a loud voice, but it's very difficult to give lectures, public lectures, and to know exactly what level to give it. And in this particular lecture, I've been thinking about my father-in-law, Mike Nissenbaum, who's a medical doctor, but a great fan of mathematics and a great appreciator of mathematics. And each time I decided what to put here, I thought, would he like it or not? And I guess we'll see. I'll send him the lecture. Afterwards, you can tell me what you think afterwards. Also, there were some tables in this lecture that were prepared by my 13-year-old daughter, Anne, who was supposed to be here, but she seems to be late. But you will be able to confront her if there are any mistakes, either there or anywhere else in the lecture. I'm copping out. Okay. Okay, I've chosen the topic of Diophantine equations partly because it is very easy to describe the problems, even though the solutions are very difficult. So, also because I've worked on some of these problems, but mainly because it's, I think, quite understandable what we're after. Diophantine equations might sound the easiest of problems in mathematics because you're trying to solve equations where the solutions are to be found in whole numbers, integers as we call them, or sometimes in fractions, which are ratios of integers, a over b. Now, it might seem that that should be the easiest part of mathematics, but because you can't divide if you're working with integers, and if you're working with fractions or rational numbers, as we call them, you can't find roots of polynomials without knowing easily, without inventing new numbers. The standard tools of mathematics, like dividing, are not available, and hence the problem actually is much harder, and the theory of Diophantine equations happens to be quite difficult, and we don't really know that much about them. So I'm going to stick mostly to the quadratic equation. It's already sufficiently difficult, and it will occupy most of the lecture. At the end, I'll point out the few things we know more generally. The main theme of this lecture is what I would call a local to global principle. And that is that if we do really invent new numbers like real numbers or complex numbers or algebraic numbers, then we are able to solve these equations. Or if we solve them in arithmetic on dividing by numbers, which I'll describe in a minute, then these problems become actually easier. So we, as number theorists, will treat the real numbers or equations over complex numbers. These are difficult problems in themselves, but we should treat them as much easier. And if we can get information about the integers by understanding what happens over other fields or other rings, we make progress. And the local to global principle, which you'll see come back over and over again, is a principle that certain easy things, and I'll keep on telling you what is easy, if they are true, then the hard things should be true, and that's supposed to be a deep step. All right, I'm only going to talk about quadratic equations, but if you ask, and this is the only slide, and this I was shocked to see in a lecture of Avi Vigdisson at the Congress a few years ago, that the following statement is true, which is quite remarkable. Linear equations are easy to understand, even systems of linear equations, where the unknowns, so linear would mean you wouldn't have a square there, and you're trying to solve, say, for x1 and x2, and even simultaneous linear equations. They are easy to solve for the x's, even in the integers. But the minute you put a square there, that's not the general quadratic equation, that's just a parabola, and you ask the following question. This is, in mathematical terms, not a difficult problem, but from a complexity point of view, which is, suppose I have as input 3 integers a, b, c, and I ask whether that equation has a solution, x1, x2, which are positive integers. The word positive is absolutely critical here. And the question is not whether you can tell me whether I can solve this, but whether you can do it quickly. That's what complexity is about. So if I represent the input A, B, C in binary digits, so that's the data you give me, and I want you to give back the answer to this question in polynomial time, meaning the number of operations you take will only depend on the number of digits in A, B, and C. That's apparently a very difficult problem. It is NP complete. It is as hard as any complexity problem. It's equivalent in its complexity to standard difficult problems. We don't know that any problem's really hard, but if there is a hard problem, this is going to be one of them. So this question already, by just putting square there, is already putting in the question of speed of computation or complexity, showing the quadratic makes it much more complicated. That's as much as I'll say about complexity. Let me now take you 100 and some years ago to the lecture of Hilbert, his famous set of problems, 23 problems presented to the International Congress of Mathematicians in 1900. His lecture was in French. This has been translated. I can't, so I assume it's accurate. Our present knowledge of the theory of quadratic number fields puts us in a position to attack successfully the theory of quadratic forms with any number of variables and with any algebraic numerical coefficients. This leads in particular to the interesting problems to solve a given quadratic equation with algebraic numerical coefficients in any number of variables by integral or fractional numbers belonging to the algebraic realm of rationality determined by the coefficients. Now, I'm not going to assume you all know what all that means. I'm going to explain what this question he's asking is. I'll explain all the terms there eventually. But I want you to note, firstly, what the question was, and secondly, he refers to 3 papers, one book of his own about algebraic number theory, which he understood would play a big role in solving this problem. The second is a paper of his on relative quadratic extensions of number fields, which was the beginning of something called class field theory, which will enter in the description of some of the elementary problems I'll describe. And thirdly, he refers to, I think Minkowski was his student, a beautiful paper, and there were a series of papers by Minkowski which changed the subject and which will impact the solution. I'm going to try to describe the solution to this problem, which has only come recently, but it's based on many things. Now, when Hilbert makes a series of problems, when he made these series of problems, his problems were very carefully thought out. They weren't just problems that occurred to him the night before and he threw out. He consulted with people, and this was based on many things that led to that. So let me step back before his lecture and describe some very easy problems that everybody should understand, and it's the generalizations of these that this is all about. which numbers are sums of two whole numbers squared? Which numbers are sums of squares? So this is a quadratic Diophantine equation. We want to solve the equation in integers. x1, x2 are to be whole numbers. And which positive numbers, well, the sum of squares must be non-negative. So which positive numbers t are sums of two squares? Well, for any given t, you can check, because x1 squared must be less than t, so x1 is less than the square root of t. There are only finitely many choices of x1. You go and you check, and checked. And this is the table. Now, there's a reason I'm only going to put t a prime there. That'll become a little clearer as we go along. But I should have put any t there. It's just the answer's a little more complicated if I put any t there. So I go through the prime numbers, which were listed here up to 100. And the solutions were found when they existed. And there's a no solution where no solution existed. And if you look at this for a moment, you'll see there's a simple rule, a very simple rule as to whether you can solve this or not. And that's simply whether t gives a remainder 1 when divided by 4, which I'll from henceforth denote by p congruent to 1 modulo 4. That just is a shorthand for p gives remainder 1 when divided by 4. So if p gives remainder 1 when divided by 4, you can actually find a solution. So, for example, I'll ignore the prime 2. 2 squared plus 1 squared is 5. So 2, 1, there's your solution. And 5 is congruent to 1 mod 4. And if you go through that table, you'll see there is no violation of that rule. And the ancients noticed this. And then the question is this a general rule or not? I should emphasize our subject, this kind of number theory, is very concrete, and most of the interesting problems emerge by looking at data. Gauss, who was a master at this, computed and always noticed interesting things, and then you want to see if these are general rules. Well, the one part is very easy to see. It's an easy side and a hard side to this, that if p gives remainder 3 when divided by 4, then certainly it's not a sum of two squares, because the possible remainders that you can get when you divide by 4 are 0, 1, 2, or 3, and if you square that and keep only the remainder, you'll get 0 or 1, and if you try add 0, 1 mod 4, you'll never get 3, the squares. So 3 will never emerge, and so if the number gives remainder 3 when divided by 4, or congruent to 3 mod 4, it is not a sum. It's not a sum of two squares. So that explains one part of that. But the much deeper part of this is if this, I will call that henceforth a local congruence obstruction. So it's in arithmetic on division by 4. I emphasize that when you do arithmetic modulo, which is just again division, modulo q, this is easy. And we consider this easy. It's not entirely trivial, but it's much easier than working with whole numbers. So if we can reduce a problem to a problem where you just have to study things in congruences, you've really made a big step in everybody's opinion. So the converse here is that the minute the prime number is going to give remainder 1 when divided by 4, then these solutions will actually be there. Actually, we're going to claim that's true in a second, but finding them is an interesting complexity question by itself. There are very clever algorithms to find them due to Scope, by the way, using algebraic geometry. Nevertheless, here we just want to know whether there are solutions x1 and x2. If you look at the history, Fermat says, yes, he can prove this. This was expected, and he says he can prove this, but he, as usual, offers no proof. I will later, I don't think I'll have time, but if at the end I have time, I'll actually give you what is believed to be his proof. It's entirely elementary by his method of descent. This is elementary if you know a little bit of math. So in general, if I have an equation where the coefficients, it might be a polynomial equation, polynomial expression like this, we call it quadratic form. We can stick to that for the time being. And I want to solve f equals t in integers. So I call that global, meaning I want to solve over the integers. If there is a solution to that, there will have to be a solution in arithmetic on division by q, in arithmetic modulo q for every q. It may look like we've taken a hard problem and make it harder because this is for all q, but these kind of equations, I repeat, can be studied mod q, and only finitely many q's have to be worried about in any time, in any given moment. So this is easy, that's hard. But we notice if there's a solution in integers, there must be a local solution. And what we would love is if this is true, we can go back. And that's what's happened here. As long as this property passed, that P was congruent to 1 mod 4, all of a sudden we want to prove, and that's a big step, and Fermat claimed that, that there are integers x1 and x2, such that this is true. Another way of saying it, now allow any t, if you want to solve x1 squared plus x2 squared equals t, you can solve that if and only if you can solve it in congruences. And this you can answer in terms of progressions here, or factorizations of t, and this then is the solution to this problem. So this is pre-Hilbert, and if you've seen a sum of 2 squares, why not look at a sum of 3 squares? It's already less elementary. Which numbers are sums of 3 squares? Again, we're going to do the inspection. Now they are not just one solution each time, and I don't restrict to t being prime. But I'm only interested first, is there a solution, not the number of solutions. So the dot, dot, dot says there are other solutions. You can permute the solutions. Again, you go search. If you look at this table, you'll see most numbers are a sum of 3 squares, but you'll see 7 isn't, 15 isn't, 23 isn't, and 28, which may be a little surprising, is also not. So the first 3 are obvious again, because if I look, you have to guess which modulus to work with, but this time you look modulo 8, and in each of these cases you have to find the right modulus, which tells you the local congruence obstruction. The squares of the numbers modulo 8 are 0, 1, or 4, and you can't add, the remainders are either 0, 1 up to 7, the squares are only 0, 1, or 4. If you add 3 of them, you'll never get 7 in arithmetic modulo 8, so you can't have these numbers as a sum of 3 squares because there's a local obstruction. And in fact, 28, which is 4 times 7, is also not a sum of 3 squares, if you check. And the same argument, just jazzed up a little bit, will show that any number which is of the form remainder, so either remainder 7 when divided by 8, or 4 to the a times any integer a, times a number which is of that type, will never be a sum of 3 squares. So the local congruence obstruction is you better avoid these numbers. But now it's a much deeper theorem that once you pass that obstruction, you are a sum of 3 squares. And this is a famous theorem. The history of this is interesting. Legendre claimed it in 1798, but he didn't have an unconditional proof. He had to assume something which hadn't been proved yet, something called that they are a theorem that came much later about primes in progressions, a theorem of Dirichlet. But he had the right idea, so let's put his name down there. But the first official proof is due to Gauss. So what Gauss is doing is quite remarkable. He's saying that as long, and Legendre, as long as you take a number and as long as this local obstruction, which you easily discover, is passed, is not, so as long as you're not of that form, then they are magically a solution to this equation. This doesn't, as I say, have a completely easy proof. If Legendre couldn't find one, and Gauss, by the way, if you read the entry in This Question is Arithmeticae, which is where he describes this. He describes this with the same theorem about sum of 3 triangular numbers, and he writes Eureka. I think he's really proud of this theorem, because I think many people were trying to prove it, and he was the first to give a complete proof. I'm going to state a theorem that's going to contain all these things, very easy to understand as special cases. So there's, from my point of view, there's a general reason for all this. Moreover, so the more squares, the easier the problem. The more variables in your quadratic form, the more chances you've got to solve it, at least crudely. And so it should be easier. And an earlier theorem, which is a well-celebrated theorem, is that every positive number is a sum of 4 squares. For that, there are no local obstructions, and every number is represented as a sum of 4 squares, a theorem of Lagrange. Now, Conway, who's quite a genius at taking these old things and giving a new twist to them, formulated what is now called the 290 theorem. This is a very recent theorem. It was only proved 2 years ago by Bhargava and Hankey. Bhargava is a colleague of ours at Princeton. Hankey was a student at Princeton. Conway is a colleague of ours. Scheenberger was a student at Princeton. Anyway, so it's, I think, a Princeton math department theorem. And it says, it's quite, I mean, the question is, people have studied, are there other quadratic forms for which every number is represented by the form? At a technical level, I'm going to only stick to what are called positive definite quadratic forms. These numbers are only split out positive values here. Let's pretend that's what it means. Just everything can be done more generally. I just want to stick to this finite case where everything is nice and finite. And the 290 theorem, first formulated by Conway, is that if you have any quadratic form in the world, and it's to represent all numbers, then of course it better represent these first few numbers that I've written down there. Those are not all the numbers up to 290. That list is very carefully contrived to have the following property, that if your form represents all these numbers, 290 being the last one, then it will represent every number. That's your certificate forever. So it's a lovely statement. It's not that hard. I mean, it's not easy to prove, but it's the formulation is quite striking. And there are many forms in 4 variables that are today called universal forms, which share the property of sum of 4 squares, and they represent all positive numbers. They actually, part of the proof of this theorem, or the consequence of this theorem, is to write down all those forms, all those universal forms, which have the property that they share with this. Every positive number is represented. And the way to check it in each case is to just check this finite list. And that's a finite calculation. So it's interesting you can breathe new life into such an old problem, and that's one of Conway's remarkable talents. Okay, so you might feel that we just always have this local to global principle. It seems very easy. The moral, however, is if you just change the problem slightly, everything goes bad. Euler worried about it, Ramanujan worried about it, and the problems become very difficult, and that's really solving the quadratic equation is what Hilbert's problem is all about. Can we decide which numbers are represented? Can we solve a quadratic equation? I'm looking at what's called a homogeneous equation. The passage from there to the general case is not difficult. So I give 3 examples to show you now that this local to global principle fails very quickly, and that we were looking, and these old friends of ours had found the very few special cases that are nice. But don't worry, the moral of this whole lecture is everything is nice in the end. So let's take, instead of x squared plus y squared, let's take x1 squared plus 27x2 squared. I just put 27 there instead of 1, and ask which numbers are represented. And instead of taking a sum of 3 squares, let me put a number 10 there. This was done by Ramanujan in 1916. Euler, I don't know exactly when, but clearly when he lived. And let me put down immediately what is the most difficult case of the Hilbert problem, which are which numbers are sums of 3 squares. Now, if you remember that thing I read out that was translated, it said to solve the quadratic equation over a general number field. Minkowski had already done most of the groundwork where the variables are to be just ordinary whole numbers. So I'm not going to introduce to you a general number field. There's no point. Let me just introduce one number field, or one sequence of number fields, which have all the difficulties of the most general case. And that is, instead of looking at just whole numbers, I'll look at whole numbers of the form m plus n times 1 plus root d over 2, where you formally multiply and add, where you just use that d squared, root d times root d is d, where m and n are integers. And here d, I'm going to assume, for reasons that will become clear in a minute, is square free for simplicity. That means it's got no square factors in its prime decomposition, and that it's congruent it gives remainder 5 when divided by 8. Now, if you ask in this ring which numbers are sums of 3 squares, the same question that Gauss answered over the whole numbers, this problem is as hard as the general case, and I will describe its solution. All right, let's see why these cases are difficult, or at least they're different. So if I take x1 squared plus 27x2 squared, ignore this. This is another form which only somebody who knows the subject, who is very clever, could produce. If you could produce this with knowing nothing, that would be quite remarkable. But there's a companion form here, which I will bring back later. Just ignore it right now. Let's just take x1 squared plus 27x2 squared. We're obviously going to run into problems, because 27 is big. And the only local congruence obstruction, if you make that calculation like we had before, so we work in arithmetic modulo NEQ, you'll find the only obstruction is, again, I'll stick to primes in this binary case when they're just 2 forms. The only obstruction is that p had better give remainder 1 when divided by 3. But if you look at 7, which gives remainder 1 divided by 3, there are no solutions. 13, there are no solutions. Well, of course, if you give remainder 2 when you divide by 3, there will be no solutions for congruence reasons. But these guys are well, these guys don't obey our local to global principle. They omit what we are expecting a solution there. Just to see a little bit where I'm going, notice that every time this guy omits it, that guy knows to put it. So this local to global principle somehow is resuscitated with this friend of it. But right now we're just looking at this column, and we see that it's just simply not true. And we may wonder which numbers are represented by x1 squared plus 27x2 squared. It doesn't have such a simple answer. And Euler asked that, and people have asked that about, and Hilbert's asking this about any form in any number of variables. The Ramanujan form is a little more interesting, perhaps, or this is not uninteresting, but maybe more familiar. This is a little less familiar, and it proceeds as follows. I will not only look at odd numbers. Ramanujan looks at both even and odd numbers. Turns out that if t is odd, there's no local obstruction. I guess I should put up the Ramanujan form again. The Ramanujan form is this one. x1 squared plus x2 squared plus 10x3 squared. For which numbers t can you solve this in whole numbers? x1, x2, x3. I'll only stick to t odd, then there are no local congruence obstructions. I make this statement glibly, but I assure you that with a little bit of mathematics, these are easy things to answer. They're not difficult to determine what the congruence conditions are. And so he computes that, and he notes there's no obstructions. But then he observes that there's a list of quite a few numbers there which have no reason not to be represented in terms of congruences, but they aren't represented. Remember, you only have finitely many chances to represent this, and if you don't, you don't, because the form is x1 squared plus x2 squared plus 10x3 squared. The x's are limited. They're whole numbers. So he observes that these numbers are not represented, and he says they don't seem to obey a simple law. Later, 2 more numbers that aren't represented were found, and then people have searched on a computer up to about 10 to the 10, and there are no further exceptions. I would like to say I know the answer to this question. Of course, a general theorem, I say we can solve this. One of the highlights, I'll tell you to what extent we know the answer to this in a moment. In any event, this was his question. Now, if Ramanujan says that there's no simple law, there's probably no simple law, because that's one of his great strengths, is to actually look at numbers and tell you what the law is. So he didn't go very far, and he didn't venture out to conjecture that maybe eventually there are no more exceptions. But we will answer that question. So if you look at the sum of 3 squares over any ring of integers of the type I described, so that's my example of a number field, then you can ask these questions, and they all have this feature that they are at least finitely many bad guys. In other words, finitely many numbers which are supposed to be represented because there's no congruence reason not to, and yet they aren't represented. There's one exception. There's one field in which a sum of 3 squares is better than all other fields. And this is a theorem of mass, and I'll explain, you'll see in a minute why it's true, that every positive number, in this case it has to be what's called totally positive, because if I have a number in this field, both it and its conjugate, for those who know what that means, must be positive, every positive number is a sum of 3 squares. It's better than the ordinary whole numbers. But besides that, there aren't any other fields with that property, and the question of which numbers are sum of 3 squares was a much-studied problem asked and studied by Siegel, who's I will come to. I think the main contributor to this Hilbert's 11th problem is Siegel. All right, I have been talking only about integers, and if you look at any text, it will usually say that Hilbert's 11th problem was solved in 1921 by Hasse. That's what this common belief is. And that's because people have interpreted it, I put it up for that reason. He said to solve over integers and over the rationals in a field. The integers was his first question, and that's much, much harder, and that's what I'm discussing here. The solution in rationals is easier, simply because you can divide and you can do more operations, and there's good reason that that should be easier. And for that, there's an absolutely stunning and beautiful principle. And that's called the Hasse-Minkowski theorem, and considered to be, and Minkowski had proved some of this for the rationals, and Hasse gave a complete proof of this theorem that I want to state here. I'll just explain it in a second. And this theorem is as good as a local to global principle, so good that when this happens for other equations, we say the equation has a Hasse principle. It's so good. Hasse used, Hilbert had great insight. He said, you will probably have to use my theory of relative quadratic extensions and class field theory, which he was the father of. And that's one of the, of course, key ingredients in Hasse's proof. The solution, I'll just state it for Q, that's really Minkowski's case, is so beautiful that let me state it as a clean theorem. Suppose I have a quadratic form. Everything I've been writing down was a quadratic form. So any expression like this, I can have cross terms in any number of variables, but where the coefficients are now to be fractions, rational numbers rather than whole numbers, and the number on the right-hand side, t, is to be a fraction. And of course, to make it fair, I'm also allowed to find x, which is a fraction. So I want to solve this in rational numbers. Well, most engineers know that they're the rational numbers and they're the real numbers. Somehow we take the reals for granted and we think it's obvious, but there are other numbers that I'll mention here and will not try to define. I don't want to make this a lecture outside this audience. But it's certainly true if I want to solve this over the rational numbers, if I want to find an x a rational number, I better be able to solve it for x a real number, whatever we mean, and we all seem to think we know what real numbers are. And these quadratic equations over real numbers are very easy to answer, to solve, to decide whether this has a solution by what's called Sylvester's theorem of inertia, for example. Well, it's not enough if you're looking for rational solutions to only look at real. That's a necessary, a local obstruction would be there's no real solution, but similarly there are other numbers called p-adic numbers, which are other kind of generalizations of the rational numbers. And if you have a rational solution, you better have a p-adic solution. And to decide this equation over the p-adic numbers is again a straightforward exercise. So deciding whether f has a real solution or p-adic solution, which is an absolutely necessary condition for solving over the rationals, is easy, and the remarkable theorem is the clean local to global theorem, no counterexamples. If you can solve this over the reals and the p-adics, you can solve it over the rationals. It's a deep theorem. It's as good as local to global can get. And it would be lovely if there were more equations with this beautiful property. All right, I want to get back to integers because that's the theme, and that's really what, so that's half, I would say, the easy half of Hilbert's 11th problem. The hard half is to solve it over the integers, and it was Carl Ludwig Siegel, and I want to explain to you a beautiful theorem of his, who made, in my mind, the main attempt on this, even though he didn't quite get to the very end. We stand on his shoulders at the end, obviously. And he was a professor here from, I think, about 38 or 1950 or something. And in fact, this theorem was proved shortly before he came here. This is from 1934. I want to describe his work, and it's quite easy to understand because it's all just about local to global principle. So the first thing, this already was known to Gauss and Minkowski, is that Siegel says there are some mysterious companion forms. You might want to understand f equals t. That's what we want to understand. I already gave you a hint. There was a companion form in the one table. There are a finite number of other forms which, in terms of congruences, are entirely indistinguishable from the form that you're looking at. They are, so for example, if you want to solve how many solutions are there in x, all the x's, so this is any number of variables, all the x's are to be determined in arithmetic modulo q, so the x's go between 0 and q minus 1, each separately, and I ask how many solutions are there in this arithmetic modulo q. That's a finite number. That number will not depend on j. In other words, these f's have the same number of solutions, but that's not their definition. Their definition is that they are locally the same in a suitable sense to the f. Most importantly, for any f, you can compute these other f1 up to fh explicitly in any given example very quickly. Well, I shouldn't say that. I haven't had that much experience, but you can compute them. I wouldn't say Avi will scream at me, well, how many steps? I don't know. It's effective. And in any of these examples, I'll give you what these other forms are. And now the theorem, which in its cruder form reads as follows. That if your original equation, this is where we started, we want to know which numbers are represented by Ramanujan's form. Pretend F is Ramanujan's form. What this says is there are these H companions, H is called a class number. There are H companions such that if you can solve this in congruences for every Q, then you would like this local to global principle. You would like to be able to solve it in integers, but this says, I can't quite guarantee that. I can guarantee that you can solve it for at least one of its companions. Maybe for it, but for at least one of these companions. So you're not in bad shape if you take this set altogether. And of course, you're in great shape if this number is 1. If there's just one form there, and we can compute that in any example, then we have a local to global principle over the integers. All right. And let's look at our forms. What are the numbers associated with them? So, for example, sum of two squares, the reason Fermat and people before him had such a nice answer is, of course, h was 1. You can compute that. And for sum of three squares, h is 1. And for that miraculous form, q root 5, that ring of integers, h is also 1. Unfortunately, as Siegel points out very quickly, h is almost never 1 for... There are only finitely many forms in the world for which h is 1, even if you go over number fields. So you're going to have to entertain h bigger than 1. Let's go back to x1 squared plus 27x2 squared. The companion form that you compute is the one here, and you see the theorem in action. That's the companion form. Every time, the arrows here where you're expecting a solution, every time you failed here, the other guy succeeds. Every time here that you fail, this one succeeds. So the theorem works in this example, up to that number. But it's a general theorem. And of course, Ramanujan picked up that form. Whether he knew this theory or not, I'm not quite sure, but he quickly saw that he was missing numbers. I didn't see in his paper him writing down the companion form here, the second form, which is like the other piece of the puzzle. All right. Now, Siegel did more. The real bottom line in this lecture is, how do you really produce integer solutions to equations? You can't sort of write down the square root of something like that. There are techniques from Galois theory for special equations, Galois cohomology as it's called. But by and large, we have very few powerful tools to produce integer solutions. And the one powerful tool is to count. The reason they're solutions is because there are many solutions, which is certainly not happening in this example. So this will succumb to algebra, and we have three or more variables, it'll succumb to something else. So I want to show you that Siegel actually went further, and this is the only part in the lecture where I'll actually mention calculus for a moment. So those of you who don't know calculus, you'll have just a picture of what I'm talking about here. That's the maximum I demand. What he says is, maybe I can recover the number of solutions by just looking at the solutions in congruences. Maybe I can resurrect the whole story just from that. So the idea is, let me count the number. So remember, our given f, which is indistinguishable from its neighbors or its companions. For our given f, let me count the number of solutions to f of x equals t. And now instead of taking q to be any integer, I'll take q to be a prime power. So for each fixed prime, maybe p is 3 here, I count the number of solutions to f of x in arithmetic modulo p to the k, 3 to the k. If you think about it, you should more or less expect there to be p to the k to the n minus 1 solutions, because I have one equation in n variables. So this ratio is the number divided, so to speak, by the expected number. And that should be close to 1 maybe. So you take this and you do this and you make the power get large. If you're not comfortable with that, don't worry about it, because this is not a serious limit. This limit is attained usually with k equals 1. Happens very quickly, except for the prime 2, where everybody gets it wrong, by the way, including Minkowski, as Siegel quickly points out in one of his papers. He says, I refuse to compute this at the prime 2 because people will be writing papers forever, which they are, correcting it. Not him, because he never put anything down. He was smart enough. In any event, you compute this number, which is a local thing and is easy to compute. So for each prime t and for our number t, we compute this number, which is, this will be a whole number, and this will be a whole number, so it's a fraction. It'll be close to 1. And there's no reason that we shouldn't try to count the number of solutions to f of x equals t in the real numbers, because it's also part of our game. And so we compute the volume where f of x is close to t, within epsilon, divided by 2 epsilon. So this is some volume of some kind of shell with 2 ellipsoids. And we divide by epsilon, take to 0, and we get a number which is the density at infinity. This is the density at each prime. Let me show you, these are easy to calculate. So if I have x1 squared plus x2 squared, and I'm computing this infinite volume, this is just an annulus, and if you use the area formula for the area of a circle, you'll get that this limit is pi. So this looks crazy. I'm trying to solve the number of solutions to a whole number equation. I'm going to give you a formula for it. And the number pi came. He's going to use pi, which is a highly transcendental number in the formula. I'm leading to his famous mass formula. It's very easy and beautiful. You do this for this x1 squared plus x2 squared. These are easy to calculate. I calculated them. You get that at the prime 2, it's 2. At the prime p, it's 1 minus epsilon p over p, where epsilon p is 1 if p gives remainder 1 when divided by 4, and it's minus 1 otherwise. So for each prime p, and for the infinite prime, we can compute this. And now there'll be a special prime, because I'm writing x1 squared plus x2 squared equals t. So when I come to that number, I might get something a little different. So I'm assuming that t is congruent to 1 mod 4, because after all, that's where I'm going to pick up this congruence obstruction if I were trying to compute the number of ways of writing a number as a sum of 2 squares. In any event, you'll get this number. So that's all local calculations, and now I can state a very beautiful formula which we can understand completely. We're going to count the number of solutions, not just whether there's a solution. We take all the companions, and we let r f j of t be the number of ways you can, number of solutions to f j of x equals t. That's integer. And his theorem says that as long as you sum, this is why it's called the mass or average over the companions. So notice if this wasn't all there, this would be the sum of r f j of t. There's some integers. There's some symmetry that's coming into this problem. Symmetry is at the heart of all of this group theory. I've given you no proofs. So it's not surprising. These are finite groups, orders of finite groups associated with these quadratic forms. Anyway, this is for a given f. We compute f1 to fh. These are all fixed numbers. We want to understand these as t is a variable. This ratio, which is a global count, averaged in the sense over all of the companions form what's called a genus, is equal to the product of these solutions over the real numbers and over these local densities. And this number beta is either a half or 1. So this is a grand generalization of knowing whether you can solve it. This infinite product here over all the primes converges. It makes sense. And if any of the factors is 0, that means there was a local congruence obstruction. So you can't solve, and there you can't solve. On the other hand, by looking just locally, this number will be not 0. That means that this average will be not 0. That means that, again, in a quantitative form, at least one of the fj's solved my equation. So this is a quantitative version of a local to global, and it's a driving kind of theorem that we have in the subject. We'd love to have generalizations of this theorem, and this is called the Siegel mass formula. Just to show you that it counts the number of solutions to x squared plus y squared equals t, that's why I computed those masses. We have to see that the number pi disappears, because on the one side, the number of ways of writing a number t is a sum of 2 squares. If t gives remainder 1 when divided by 4, we know by Fermat, if he really did prove it, that it is a sum of 2 squares. Then you'll have x1 and x2. They're basically unique. You can switch x1 and x2. They can't be equal, because 2x squared will never be a prime, because of the prime. And they can't be 0, so that you'll get 8 solutions. So since I told you the class number, this h for the sum of two squares is 1, this will give me an exact formula for the number of ways of writing a prime as a sum of two squares out of the strange product. And remember, the Archimedean, the real solution, was the area of a circle, which was pi. That came in. So there's a pi there, there's a 2 from that, there's a beta, which is 2, that's that. And then the local masses, I computed them, will be this product. And that product, if you write 1 over that, that's the series over here is 1 plus epsilon p over p plus epsilon p squared. Epsilon was plus or minus 1, depending on whether p was 1 or minus 1 when divided by 4. So the bottom here is 1 minus a third plus a fifth minus a seventh, and that's the only thing I want you to remember from calculus, that that's a number pi over 4, arctangent of 1. And pi cancels, thank goodness, the top and the bottom, and you get 8. Well, you might not be so impressed with that one example. That's a completely general theorem. Always true. So that's the famous Siegel mass formula. But as Siegel points out, it doesn't solve the problem. It only solves the problem if you insist on averaging. Well, it should be 99% of the way to the solution if you think as follows. In the case n equals 2, which I'm going to dismiss very quickly, in the case n equals 2, that's two variables, the right-hand side doesn't grow. We've just seen that the number of ways of writing t is the sum of two squares is only 8 if we're going to succeed. So counting, if we count, we better count accurately. We got no room for error. But if n is bigger than 2, then this product of local masses, so all the local stuff I treat as understandable, and it's quite easy to see that this part is, well, that's a subtle point, I'll get back to it, but it's really not too serious, and this will grow handsomely with t, roughly like t to the n minus 2 over 2. So if n is 2, it doesn't grow, and if n is 3, it'll grow like square root t, which is roughly the number of ways you expect to be able to write a number as a sum of 3 squares. So crudely, this is giving you the growth rate. And so if n is bigger than 2, we shouldn't panic. We should still be able to solve this problem by saying that when t is large, well, maybe all of these guys, together they represent the number, but maybe each one will do it roughly the same number of times. We have a chance that there's some democracy there. Okay? When n equals 2, it's going to be a problem. But luckily, when n equals 2, we can use algebra. And this, Hilbert was exactly pointing in the right direction. This is class field theory. So for example, if we have just two variables, we can always factor into linear factors by increasing our numbers in the way that I was describing when I described one ring of integers. So as you can factorize that, where that's the square root of minus 27. And now we want to write the product of two numbers, and that's why at the beginning I only gave you the answer for p prime, because it was much simpler. So you're now asking, is a prime number a product of two integers in some order in a ring in a bigger field? And that's a divisibility question which is beautifully answered by class field theory. And it's answered by reciprocity laws, and you can in fact give a much more complicated answer to the question of which numbers are represented, but the answers get very complicated quickly. Just to give you an example, with x squared plus 25 plus 27 y squared, which we saw that table was deficient for a while, and then there was this companion form. Well, can we work out a local condition which tells me which guy is going to give me the answer? And this was actually discovered by Euler, but the class field theory generalizes that. This just uses what's called cubic reciprocity. First proved, of course, almost everything by Gauss of this type, is that the other condition you have to write down is that you can solve, so these are purely local conditions. There's an extra condition. You better have a cube root of 2 modulo p. So you must be able to solve in arithmetic modulo p, which I'm considering as a basic in this lecture. That's the extra condition. So in two variables, you can solve this way, and algebra does the trick, and the problem is solved. So now let's stick to n more than 2, so 3 or more. And Siegel, who was really eager to solve this exact problem, solved this for n bigger than 4 early on, even before Hasse, or roughly around the time of Hasse's theorem. By the way, the Siegel mass formula, everybody says they're giving you the correct conceptual proof, including me. I have a paper with Rudnick and Eskin saying this is the real conceptual proof. Conceptual means simply, I'm familiar with these ideas, so I like them. There's nothing wrong with Siegel's original proof in 1934. It was perfectly beautiful. It's, as he says, the longest completion of the squares following the Babylonians ever done. It's a whole book, but it's elementary, actually. Weil wrote a whole book giving a proof of that Siegel formula too, relating it to Tamagawa numbers. Okay, so back to Hilbert's problem. Siegel solved it if over any number field if the number of variables is bigger than 4. The case of 4 was more difficult, was solved by Kneser by a rather brilliant idea, elementary pigeonhole argument using Hasse. All this uses Hasse's theorem already. Everything does, yeah? And the hardest case is n equals 3. And in fact, as you'll see in a moment when I describe what we know, in that case, the solution is a little bit flaky at some level. Anyway, for n equals 3, Linnik introduced some really ingenious ergodic theoretic ideas to try solve this. And he solved some other problems, and these have been revisited recently. But he wasn't able to solve this particular problem, and so far his methods have not been able to work in this case in general. The real breakthrough was a lovely breakthrough of Ivanić in the theory of modular forms. So far I haven't described the techniques, but mostly Siegel in this proof, it's all elementary. Now we start to bring in much more modern machinery, and Ivanić made an important breakthrough, and then Duke and Schulze-Pilot solved this problem of 3 variables, the theorem I'll state in a second, which is valid when the coefficients are integers. And the general case of a number field required further ideas and different methods, and that was solved completely by Cogdell, Piatetsky, Shapiro, and myself here a few years ago while we were visiting here. And even now people are working on improving these things, and Akshay Venkatesh, a very young mathematician, has found a variant treatment which has certain advantages. And here's the theorem. So here's a solution and the caveat. So there is a local to global principle in general. So the hardest case with 3 variables, and I'll tell you what's bad about the 3 variables in a second. That is what you thought should be true is true. So in Ramanujan's form, there are only finitely many exceptions. There are, after some point, no more exceptions. There is a local to global principle if you wait long enough. That is to say that if you can solve the equation in congruences, and if t is large, and in the number field t large has a meaning, so there are finitely many bad guys, because after all, these Siegel's formulas already telling you 90% of the answer. You have these h competing forms, the number's small, you don't know which one's going to represent a small number, but when t is large, there are many, many possible ways to represent it, and they all participate simultaneously, democratically. That's what's proved, actually. So there is a local to global principle over the integers as well, as long as t is large. That's a clean theorem, because after all, I just tell you, all right, if you want to know a given f, take Ramanujan's form, you tell me how large it is for this theorem to start to work, and we're done. And then I check by a computer up to 10 to the 10. There's a little rub in 3 variables in this proof. This proof is sufficiently tricky, let's say, and complicated and relying on all sorts of things, that it does not tell you what sufficiently large means. What it really says is there is a point after which there's at most one exception for Ramanujan's form. So that means there's either no exceptions, in which case we're happy, or if there's one exception, the theorem's true beyond that exception. That's what's really proved. And Conway, who wants to use this theorem, says, well, that's completely useless to me, because I want to know what numbers Ramanujan's form represents. So what's really proved here is that eventually things are good, but I can't tell you, it's not effective, the proof, when that kicks in. That's only a bad feature in 3 variables, which indicates, at least in our present understanding, why it's a tough problem. So this is this non-effective, and it solves all problems non-effectively. And that's unfortunately where it stands. However, do not think you're going to find another example beyond 10 to the 10 that Ramanujan or somebody may overlook. Because there is a sort of another problem on Hilbert's lists called the Riemann hypothesis in a slightly generalized form that if it's true, then there are no exceptions. Then the proof's effective. And it's in fact the progress we're making here is precisely to get a handle on problems that Riemann implies, but not relying on Riemann. By the way, you can get if you solved Riemann, you would have the pleasure of solving this along the way, and many, many other things. You will also get $1 million from the Clay Math Institute if that's not enough pleasure for you to solve Riemann. I don't know many mathematicians for whom that is an extra motivation. All right, I was going to say a few words about, let me just say that the mathematics that comes into the proof, all those techniques are modular forms, and in particular, the connection is immediate, at least. This goes back to Jacobi, a contemporary of Gauss, or soon after Gauss, that if you take your form, say, in 3 variables, and you make this weird sum called the theta function, this infinite sum, you get a function of z which lives on some surface, or in general over a number field of variety, and you have to study the sort of harmonics of this variety in trying to understand this problem. And this is where much of the modern work is going on. So I just say the words that go into this proof. We need the spectral theory of this vibrating manifolds. Somewhat unexpectedly, for the mathematicians in the audience, this is purely a holomorphic problem, but the entire spectrum enters in its solution. There are various identities we have to use due to Waltz-Berger. I wanted to mention his name. The big central problem is the subconvexity problem for automorphic L functions, which we have made progress on. This is something Ivanich, myself, and our colleagues and students have studied quite a bit, and this is a typical application. All right, I want to end with one generalization. It'll take me another 2 minutes. I'll be in time. That this Hasse principle is what we really would love. I give you a more general equation, like a homogeneous form in higher degree, not just quadratic. That's the story of a quadratic. It's all but solved. It's just solved except for the effective issue over the integers. Now let's take a more complicated equation or system of equations. Well, many times it's almost anything you pick up, we can say nothing. But there are forms, if you have sufficiently many variables, there's one sort of general principle to produce integer solutions by counting called the Hardy-Littlewood circle method. And as you saw, Siegel solved this problem in 5 or more variables. In fact, he used the circle method. And the moral of the story is if you have sufficiently many variables, you can handle these kind of problems. The thing about 3 variables was it was very few, and you couldn't do this by any general principles, and this modular forms came in. Now, as I said, I want to end with something which I think is one of the most beautiful local to global principles. Let's take the simplest not quadratic equation. That's a cubic equation. And that, in its simplest form, reads like this. I take the equation y squared equals x cubed plus ax plus b. We're not that ambitious to solve over integers. Let's solve over the rationals first. A and b are fixed rational, ordinary rational numbers, and I want to find solutions x and y which are rational numbers. Now I can't write this problem down without pointing out that there's a beautiful further structure known, I think, since the Greeks, that if you have 2 solutions, x1, y1, x2, y2, that satisfy that equation, you can produce a third one. If you draw the curve, it's by tangent and chord construction. You can add 2 points and produce a third point which also has rational coefficients. You are doing division when you make this new strange addition on the curve. So the points don't just come as a set, they actually have a structure of a group. And the most basic question that everybody wants to understand here is, does this have infinitely many or finitely many solutions? Can you have a local to global principle? Now, just to show you how concrete our subject is, and this was impacted by the arrival of a computer at Cambridge in 1960 with the cards. Birch and Swinnerton-Dyer apparently was a very good writer of programs, so he says, so you say also, decided to look at whether there is an analog of Siegel's mass formula for this equation. In other words, can I look at this equation locally and see from solving the equation in arithmetic modulo p whether that has infinitely many solutions? So what they did is they found clever ways to compute the solutions to this modulo P. And also they have methods to decide for any given elliptic curve, as that's called, whether there are infinitely or finitely many solutions in any example. So following Siegel, as they say, let NP be the number of solutions such that where x and y are ranging in arithmetic mod P. P is large. And let delta P be the expected numbers, P the way I'm writing it, and let that be that ratio. That's a local density. And following Siegel, let's take the product of the local densities and hope that that tells me something. And of course, if there are many rational points, you might expect there to be a bias of the solution. So maybe NP is getting bigger, a little bit more bigger than you expect. So they took the product P up to x a large number, they computed these numbers, and checked whether that grows with x or not for thousands of curves that they inspected. And they found a general rule that this goes to infinity with x if and only if E has infinitely many rational points. In other words, this is a local to global principle. They then reformulated this with some, I think, help of others in a much better way in terms of special values of L functions. Quite remarkably, the conjecture they made is only recently, since the work of Wiles, Taylor, and others solving what's called the Shimura-Tanayama conjecture, is only recently that this conjecture actually makes sense. It didn't even make sense as stated. This made more sense, actually. But today there is a very precise conjecture. It's a well-celebrated Birch-Winnet and Dyer conjecture, and it is the analog of Siegel's formula for an elliptic curve. This too finds its way onto the Clay math prize problem. If you can solve this Birch-Winnet and Dyer conjecture, you would get $1 million. And there's a way, by the way, to get $2 million. Let me just give you that algorithm. It turns out that this conjecture has been neglected. There's an exact form of this conjecture that they put forth that looks very hard, that this actually is asymptotic, as we would say, to a constant log x, it grows very slowly, to the rank, which I'm sure is true, by the way. And if that's true, that you can show formally implies both the Riemann hypothesis and the Birch-Winnet and Dyer conjecture. So if you solve that, you would get $2 million if they're honest. I do not recommend that as an approach. Thank you. I guess I'm supposed to take questions from non-mathematicians, maybe mathematicians. Okay, maybe Mike Nissenbaum will not be quite happy. We'll see. Ah, yeah.
So what is the next problem in this area that you'd like to see solved?
Well, as you saw, there's this all-powerful Riemann hypothesis that I should say has been extremely resistant. And one of the beauties of it is, firstly, it has these kind of applications. So for a professional, you would sort of prove hundreds of theorems by proving one theorem, which is kind of, if you're into putting medals on proving theorems, it's attractive. It's also fundamental. So that's the problem that would allow you to make that ineffective. But to be honest, I have not seen in any written, anything published, anything that resembles a really promising idea. But I think your question is, what would I like to see solved? Yes, and if it was someone here, it would be even nicer. The closer to me, the better. That's what is. It's interesting if you took. I spoke and the Birch-Winnet and Dyer came up. I should have said that the Riemann hypothesis is Hilbert's problem number 8. It's in his list. It is interesting to look today and see how much impact those problems had. And you could ask why. Is it because he had such insight, or was it because people were so eager to solve it? It does seem he had a great insight as to sort of what are good problems, so that each time, but this was not true of all the problems, but each time you solved it, you had to advance the subject in a major way. And I was using this Siegel as an illustration. Siegel really understood, I think, the 90% of this problem. And as you can see, this mass formula is as good as the local to global principle goes. Now, if you take other equations, I could spend another lecture on just how equations are divided up, when we expect only finitely many solutions. But these are all wild conjectures. We have very little evidence to most of this, I'm afraid. And very few tools to produce integer or rational solutions. Very few tools. Yeah.
Is there an easy way to find the companion functions?
I wouldn't say it's easy, but it reduces to a finite calculation. So there's, it is a problem where you have a finite big region, and it's purely algorithmic, what's called reduction theory. With two variables, the answer is absolutely yes. There's something called the continued fraction algorithm, which is very close to this reduction, which Gauss knew, and which is very mechanical. You start with your ABC, which you want to know what the companion is to your given guy. You move ABC into a region where you just look for solutions ABC with some inequalities, and then those the companions are just what you're staring at. And in more variables, it's a similar thing, it's just cumbersome. It's not that difficult that three variables you can do by hand, easily. But, yeah, that's my answer. It's a good question, yeah.
Can you explain somehow simply what's the source of ineffectivity in
Yeah,
your theorem?
yeah. So the ineffectivity usually comes from one man, Siegel. There's another theorem of Siegel that's being used here, and that's the only ineffective part. So in that formula, there was this remarkable identity between the number of global solutions is the product of the number of local solutions. And I said that that product, I know how big it is. It was roughly t to the n minus 2, say n is 3. So it should be roughly square root t. Now the volume term is something that's, this is calculus. That is square root t. So no problem there. But I had a product over primes. And that product over primes converges, but it could try to get very small. And just how big or small that product can be is dictated by the size of a zeta-like function, an L function at 1. And that, if you knew the Riemann hypothesis, is never too small because it controls everything. And the best bound we know is the theorem of Siegel that says that ineffectively this number's big. But effectively, nobody knows. And many of us, I'm one of the believers, I think Enrico's not, that the only way that problem will be solved is by solving the Riemann hypothesis. Some people think that you might get around that, and I've spent many years trying to do it without. Ivaniet, I think, has had, well, we thought we solved it once, but that doesn't mean it's, so the ineffectivity comes from that source only. I said the local is easy, but only effectively easy in three variables if you, well, it's not effectively known even. On the other hand, it's known if there's one bad guy, there can't be a second bad guy, and that's why you can make these rather striking statements that there's at most one exception. Ineffectivity comes in many other Diophantine equations, in Folting's theorem, in Tua's theorem. Some of these can be removed. This one shouldn't really be there because it's not something that's logically there. It's something just because we don't understand the Riemann hypothesis. That's the only reason. So that's the source. It's exactly the product of, it's the easy part that was supposed to be understood. We've done the hard work, which is how to get rid of the difference between this equidistribution that each guy is playing the same role when t is large. That's effective. Very beautifully effective. Yeah.
So you suggestively used H to indicate the number of companions. Does it have some relation to class?
No, it's by the very definition of the class number of a quadratic form is the number of companions. If you are in the binary case and you factor into this ring of integers, And if it's the full ring, then it's the class number of that field. So only in the binary case does the theory of fields and the theory of quadratic forms become one and the same theory, because you could factor it into linear factors. But if you have three variables, you can't. And it's a different theory, but the class number survives in this way. That's what Siegel is saying. There's still such a theory. All right, well, I'm available at your party.